All right, in this video, we are going to talk about voltaic cells. In other words, batteries. Like, how do they work? Okay, it's kind of the main point of this chapter as far as I'm concerned, but we're going to start going down that path, I guess. So, a voltaic cell is essentially a spontaneous, so all that stuff from chapter 18, spontaneous redox reaction, which is why we're learning about balancing redox reactions, that can produce electricity, or can produce electrons, basically. Okay, so the trick to this is, we said that if you have an oxidation half reaction, something is losing electrons, and if you have a reduction half reaction, something is gaining electrons. In order to generate electricity, you have to find a way to separate those two things and let the electrons flow through a wire. That's essentially the gist of batteries versus just redox reactions. Okay, so what you do is you separate the oxidation part of the reaction and the reduction part of the half reaction. And then you connect them with a wire so that the electrons have a way to get from one half to the other. Okay, I'm going to draw a overly detailed diagram here, or a picture. So here's an example of a voltaic cell. Obviously, if you have a battery, it doesn't necessarily look like this, but you could, in theory, make a battery out of beakers and wires and solutions and stuff. So this is what that's going to look like. So, essentially what you would need is two beakers. I'm going to kind of draw them a little wide so that I have room to label things in there. Okay. Okay. And in one half reaction, or in one beaker you have one half reaction, in one beaker you have the other. Okay. So, one half reaction that we're going to have here is zinc and zinc 2+. Those are the two ions that are involved. Okay, well, atoms and ions. Okay, so what we have is we have some sort of electrode here made out of pure zinc. Okay, hopefully that's legible. Zinc. And then this is stuck into a zinc solution. Okay, so we have the atom and the ion. Okay, great. And then over here, I'm going to draw it all the way around this side. We have copper solid and a copper 2+ solution. Okay. So, based off the last video between zinc and copper, we would expect zinc to be more likely to dissolve and copper to be more likely to be a solid. Okay. So what this means is if you threw a solid piece of zinc into a solution of copper, you would expect the electrons to transfer over, zinc would dissolve, and copper would become a solid. Well, all we're doing here is allowing that to happen. So the difference in the activity series of the metals is what drives the flow of electrons here. Honestly, the farther away they are from each other on this chart, the more easily electrons are going to flow. Zinc and copper are pretty far apart from each other. Okay. So, what we do is we connect these two things with a wire. We said that zinc would really like to give up 2 electrons and become zinc 2+. Copper would really like to receive 2 electrons. Copper 2+ would like to receive 2 electrons and become copper solid. So we expect 2 electrons to flow this way. Okay? And this is literally what a battery is you just put something in between these two, they're called electrodes, in between these two electrodes on this wire, and as electrons pass through, it can light up a light bulb or charge your phone or whatever, make your car start, whatever the battery is going to be doing. Okay. So what happens is, as this thing loses electrons, it's being oxidized, and so the reaction here is that zinc is becoming zinc 2+. And this is an oxidation process. So this is the oxidation half reaction, half cell. Okay. The electrons are just passing through this copper and they're coming into here And these ions are becoming copper solid and adhering to this copper thing. Here, these ions, or these atoms, are losing 2 electrons and becoming the ions. Okay, so over here, what's happening is the copper 2+ is becoming copper solid. This is the reduction half reaction. So essentially what we've done is we've separated the 2 half reactions, and by making the electrons that already want to be exchanged through a wire, we can create an electrical current in batteries. Okay. Here's the problem. Okay, if you glance at this, hopefully might be a little obvious here, that we're essentially just ripping electrons out of this side. So this solution is just going to get more and more and more positive, and this solution is going to get more and more negative. And electrons still repel other electrons. So if this solution starts getting overall net negative, pumping negative things in here is going to be really difficult. And if this thing gets really, really positive, removing electrons is going to get really, really difficult. So honestly, what we have drawn won't work. We need a way to balance out the charges. So what we do is we add one last little part called a salt bridge. I'm going to draw it like this. And the idea is, I guess I'll label it as salt bridge. And the idea is this just has a like a filter in here so that ions can flow through it. Okay. And what you do is you fill this with some sort of salt. For this example, we're going to use sodium sulfate. Okay. And the idea is as the positive charge builds up, we're going to need some negative to cancel it out. So the sulfate's going to pour into here to balance out these charges. Okay. As the copper 2+ becomes neutral, we're going to have an imbalance. We're going to have not enough positive charges, so the sodium will pour into this side to help balance out the charges. So the salt bridge doesn't cause the electrons to flow, but it helps prevent the buildup of charges on either side so that the electrons can keep flowing. Okay. This is a pretty standard example of what a voltaic cell might look like. Okay. Just to recap all of this, what's happening here is the zinc happily wants to form zinc 2+ because it is higher up on the activity series list. Things that are higher up on the list would rather dissolve and form, they're likely to be oxidized, form charges, formed ions. The copper is starting out as a solution, and it would really, really like to receive electrons and become a solid. It wants to be reduced. Okay. So what we do is we take those 2 half reactions, have electrodes in there, and we connect them with a wire. This thing wants to be oxidized, so it loses 2 electrons to do so. This thing receives those 2 electrons, and they kick into here, and the solution of Cu2+ will receive those and become solid. So over time, this electrode will actually get skinnier because the zinc is falling off of it, and this electrode will get fatter because the copper is becoming a solid and connecting to it. So the electrodes will actually change size during this. And to prevent a buildup of positive charge here or negative charge here, we have a salt bridge. And because this is becoming more positive, the negative ions will flow in. In this case, it's a sulfate. It doesn't have to be sodium sulfate, but for this one it is. And there is a buildup of negative charge because the positive charges are being removed, so sodium ions are pumping in. Okay, and the idea is that as long as there's salts, the salt bridge can keep pumping in ions. As long as this doesn't completely dissolve, as long as there's still solid in here, and as long as there's still copper solution, there will be a continuous flow of electrons continually pumping through. And as long, you can put a light bulb in the middle here and it'll light it up. Okay. All of these components are critically important. If you remove any of the components, it stops working. If you disconnect the wires, it stops working. If you remove the salt bridge, it stops working. If this electrode completely dissolves, which it will eventually, it stops working. If you run out of copper 2+ ions, it stops working. So you need all of it to be functional. Okay. Couple definition things here. Okay. There are 2 electrodes here. There's an anode and a cathode. The anode is the electrode at which oxidation occurs. Because it is producing electrons, it's the one that's releasing electrons, it's considered to be the negative electrode. Okay, so I'm going to label this anode. Oxidation is occurring here, it's releasing electrons, that's why it's negative, anode. This is the same prefix as anion, which is negative. Okay, the other option is cathode, like cation, same prefixes. Okay, this is the electrode at which reduction occurs. And because it's the one receiving the electrons, it is considered to have a positive charge. Okay. The difference in electrical potential, the energy potential difference between the cathode and the anode is how we measure voltage. So, if we look back at the activity series that we saw in the last video, essentially to control the voltage of your battery, like if you had zinc and iron, you're going to get a much smaller voltage than if you had zinc and nickel, or if you had zinc and copper, or if you had copper and magnesium, you get an even bigger voltage. The farther apart these are, the bigger your voltage is going to be. Okay? That's an oversimplification, but that's the gist of how it works, which means the activity series is deciding how well your battery is going to work, how many volts are going to be produced during the reaction. Okay, let's start a new page here because I'm running out of space. So, some terminology stuff here. 1 volt is a joule per coulomb. Joule is energy units. Coulomb, we haven't really seen before because it's only with electricity. It's a unit of charge. I will tell you that as far as electricity goes in this chapter, we're only really going to focus on voltage. Resistance and current, like amps and all that stuff, we're going to kind of ignore that. We're going to steer clear of it. That doesn't really come up until you start having circuit diagrams, which we are not going to touch. Okay. So the potential energy difference between the two electrodes is something called the cell potential. And the units are voltage. So the potential energy between the two electrodes, I can't write, sorry, electrodes in a voltaic cell is the cell potential. And it's labeled as E sub cell. Okay, so the gist of this whole thing is all of this is driven by the desire of things up here to become ions and the desire of things down here to become solid. So the potential energy only has to do with the electrodes. Everything else in the cell diagram is just to make the rest of it work. Zinc really wants to be zinc 2+. Copper 2+ really wants to become copper solid. The rest of this is just a mechanism to make it happen. Okay, but the voltage of this cell is entirely based off the potential energy difference between things on this chart. Now, obviously, you could shoot for really high energy, like if you had gold as an ion in a solution with a gold bar sticking off the side instead of copper, and you had potassium as the electrode in potassium ions in solution, sure, it's going to have a huge a huge voltage difference, but here's the problem. Potassium explodes in water and bursts into flames, so it's not going to be real functional as a battery. Okay, so is sodium. So really, until you get down to like magnesium, there's not a lot of functional options. And honestly, it's really hard to get things like mercury and gold and silver into solution. So really, copper is like kind of the go-to standard on that end. And like things like magnesium or aluminum or chromium or zinc or iron, whatever, those are realistic upper end things. Okay. All right, we'll stop there. We'll continue the next video here in a sec. All right, thanks.